Hello students and welcome to the calorimetry lecture. We will start by defining the specific heat of any substance, which is the heat, we refer to it as simple Q, required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Therefore, the units are joule per every gram per every degree Celsius, meaning the specific heat of any substance is how much energy you need to give that substance, so 1 gram of this substance will go up in temperature by 1 degree Celsius. So here it is. If I have 1 gram of water and my temperature was 14.5 degrees Celsius, I need to give that 1 gram of water now some heat to go from 14.5 degrees Celsius to 15.5 degrees Celsius. That amount of heat that I needed to give 1 gram to go 1 degree Celsius up, that amount is what I call the specific heat of water. So the specific heat of water, therefore, is 4.184 joule for every degree Celsius for every gram. Here is a table that shows different specific heat for different substances. You have aluminum, you have gold, carbon, water, mercury, iron. And what you need to notice here, that water does have a much higher specific heat than, for example, metals like gold or copper. And that is very important in understanding different phenomena, right? Like when you have a metal, it doesn't take much heat for that metal to go up in temperature, while you need to give water a lot of heat to go up in temperature. So that's why metals are great conductors of heat, because their specific heat is low. It doesn't take much energy to heat them. And therefore you can now think of, for example, insulators must have a very high specific heat, because by definition, what does that mean? They demand a lot of energy to go up in temperature. It's not easy to raise their temperature. The heat capacity of the matter is the heat required to raise the temperature of a given quantity. So this time I'm not really defining the mass, any given quantity of the substance by 1 degree Celsius, and therefore it will be joule for every degree Celsius. The heat capacity can be calculated if we multiply the mass times the specific heat, right? Because if you guys look at this equation here, if we said that mass has grams and the specific heat has joule for every gram for every degree Celsius, then gram cancel gram, and that will be the heat capacity, which is joule for every degree Celsius. Heat can be absorbed or released, and heat can be calculated by multiplying the mass of a substance times the specific heat times the change in temperature. So again, if I look at the units here, heat, which is joule, because heat is just a form of energy, is the multiplication of mass, which is a gram, times the specific heat, which is joule for every gram, every degree Celsius, times the change in temperature, which is degree Celsius. So if you see here, the units are canceling out, and this is here heat, which can either be a positive if it is absorbed or negative if it is released. So keep that in mind. Now the change in temperature is always calculated as the final temperature minus the initial temperature. And if heat is positive, it means it was absorbed and it's an endothermic process. If it is negative, it means it was released and it's an exothermic process. Let's look at this question together. How much heat in kilojoule is absorbed when 102 gram sample of water is heated from 3.25 degrees Celsius to 26.22 degrees Celsius. Now, let's see what they are asking. They are asking about heat in kilojoule for water. So heat, anytime you see a change in temperature, your heat is calculated by multiplying mass times specific heat times delta T. So what do you have? They did give you the initial temperature and the final temperature, which means you have delta T. Because it's water, pay attention, the assumption that you know the specific heat of water. So the specific heat of water is 4.184 joule for every gram every degree Celsius. You need to know that value. And they already giving you also the mass, so I can calculate the heat. Now, let's start the math. The mass is 102 grams multiplied by the specific heat, which is 4.184 joule for every gram every degree Celsius. They do want this though to be in kilojoule, so you can say that there is 10 to the negative 3 kilojoule for every 1 joule, and then you multiply that by delta T, and delta T here is 26.22 degrees Celsius minus 3.25 degrees Celsius. So when we do the math, and I am going to show you the outcome of the subtraction here, just because I want to bring your attention to the subtraction rule. So subtraction rule always say that I do have to keep 2 decimal places here. So the answer for this number will be 26.22 minus 3.25, 22.97 degrees Celsius. And now if this also here is 10 negative 3 kilojoule for every joule, and then here we have 4.184 joule for every gram every degree Celsius, and then we also have the 102 grams. So if I am, then this is what Q is equal to. If I am putting all these numbers together here and keeping my sig fig to up to 3 sig fig, then the answer will be 9.80 kilojoule. All good? Now that I showed you how to solve this, let's look at another question. How much heat is given off when 869 gram of iron bar cools from 94 degrees Celsius to 5 degrees Celsius? The specific heat of iron is given as 0.444 joule for every gram every degree Celsius. Okay, one more time. Q equals to mass times specific heat times delta T. The mass given to me here is 869 grams. The specific heat is 0.444 joule for every gram every degree Celsius. And change of temperature, the final is 5 degrees Celsius minus 94 degrees Celsius. Now pay attention, this is T final and this is T initial, which means this subtraction will be a negative sign, which is totally fine because the Q here is exothermic. So if I put all these numbers together and I start doing my math, .444 and times 8, 6, 9, And remember that the last thing that I need is take everything in kilojoule. The answer here will be, and I need to keep my answer in this case to 2 sig fig, because the subtraction will give me 2 sig fig, negative 34 kilojoule. All good. So now let's see the next question. Calculate the amount of energy in kilojoule released when 346 grams of steam at 182 degrees Celsius is converted to liquid at 0 degrees Celsius. In order to be able to solve this question for you, we do need to learn something that we call the heating curve. So please pay attention to what a heating curve looks like. Heating curve, in the y-axis, I do have temperature in degrees Celsius, and in the x-axis I have heat added in this direction. So two temperatures are important when you have the heating curve. The first one is the freezing point, and the second one is the boiling point. So for water, that's a 0 degrees Celsius and 100 degrees Celsius. Now, when we go up, anything below the freezing point has a solid state. So if I am here, let's assume I am at a negative 10 degrees Celsius here, and I start to add heat in this direction, then I am here gonna go up. So what's gonna happen, the temperature of my solid, because it will be all ice, right? It will increase till it's 0 degrees Celsius. Then if I keep adding heat, all my solid at 0, which is this point. So if I am looking at this point and I'm calling this point point A, or at A I have solid at 0 degrees Celsius. All my solid at 0 will be converted to B, and in B here what I have, liquid at 0 degrees Celsius will be converted to liquid. So the same temperature, but this is here in this place, in that horizontal line, I'm gonna have solid and liquid, because this is all solid at 0 at A, this is all liquid at 0, and in between I have solid and liquid at 0. When I convert all my solid at 0 to liquid at 0, and I start to add more heat, then my liquid will start to heat up till it reaches 100. So at C here, what I have liquid at 100. Now if I keep adding heat, all my liquid at 100 will convert to gas at 100. So D here I have gas at 100 degrees Celsius. And if I keep heating, then all my gas will go up in temperature in another diagonal line. This is here what I call the heating curve. Now, the amount of heat that I have in this situation here, the amount of heat that I have to get all my liquid or all my solid at 0 to be liquid, or to be liquid at 0, this here, that amount over here to go from A to B, this is what I call heat of fusion. And the amount of heat to go from liquid 100 to gas 100, this is what I call the heat of vaporization. Now, Also worth mentioning that the specific heat of a liquid water is a different temperature than the specific heat of steam. Now let's look at the question one more time, and we're going to start to have like segments with colors. They want me to tell them the amount of heat released when 346 grams of steam at 182. So the steam is right here. Will be converted all the way to liquid at 0. Remember, that is B. So I want to go from this dot right here to this dot right here, which means now we're going to color code our segments. I have to first calculate the heat released going from, let's call this A, B, C, D, this is E. The heat going from E to D, that's the first segment. And then I have to calculate the second segment, which is going from D to C. And then the third segment, which is going from C to B. So if there is a heat that's going to be released when I go from E to D, heat that's going to be released from D to C, and heat that's going to be released from C to B. Now remember, if I am going in this direction, heat is added and it is positive. But when I go the opposite direction, which is what I am doing right now, that means heat released and it will be negative. So how am I going to calculate that? Let's use the space here. I'm going to erase this part. So if I start now and I want to look at the green segment, this is a diagonal, which means there is a change of temperature. So it means that I can calculate Q by M times S times delta T. The mass of the steam is 346 grams. The specific heat of the steam is given to me here as 1.99 joule for every gram every degree Celsius. And then delta T, I'm going to take it down here, is final minus initial. And the final here is 100, D is 100, minus the initial, which is 182 degrees Celsius. So delta T here will be negative, so Q will be a negative value by itself because delta T is negative. For the second segment, I have from D to C, this here is the horizontal. There is no change in temperature. However, heat of effusion can be calculated if I have the amount of moles. And what I have here, so for the second segment, I can first take 346 grams of water steam, convert that into mole. 1 mole of water has a molar mass of 18.02 grams of water, and then multiply by the heat of vaporization. But remember, heat of vaporization is given when you vaporize water to gas. You are doing the opposite. You are condensing gas to liquid, which means you have to give it a negative sign. So it will be negative 40.79 kilojoule for every mole. And that is the second segment. The third segment, which is the orange segment, it does have a change in temperature. So Q will be calculated as mass times the specific heat times delta T. The mass here is 346 grams. The specific here is for liquid, which is 4.184 joule for every gram every degree Celsius. And the change in temperature here, B is 0, C is 100, and the change will give you a negative value, and that will be the third segment. Now, pay attention that this here and this here give you the units in joules, while the second one is in kilojoules. So you do have to unite your units add the heat of the three segments, and that will be the amount of heat released when you went from 182 degrees Celsius for steam to liquid water at 0. This is here a picture of the calorimetry, or the calorimeter that can be used inside, labs. So what you look here, I'm gonna try to point things out for you. What you can look at here, so you will see that we do have a compartment where we ignite our sample. Now the ignition will release heat. The heat will go outside of this compartment to the water surrounding the sample. Okay, now this water, we do know the mass, we know the grams, and we already know the temperature before and after, so we know delta T, and we also know the specific heat of water, right? So we know the specific heat of water. So therefore, I can tell when I ignited something or I reacted something in my ignition compartment here, it did release heat. And the heat that was released got absorbed by the water around the compartment. Now pay attention that this part here now is insulated, so the heat is all contained here and it has nowhere to go but for the water to absorb it. So that's a good way for me to know the heat of the reaction. I ran a reaction and that reaction released heat. I don't know how to calculate the heat that was released, but I have an indirect way to do so because the water around it did absorb it. Heat released equals the amount of heat that got absorbed. So if I know how much water absorbed, I know how much the reaction did release. This is a simple calorimeter that we use in the lab, and we use just a styrofoam. We mix a reaction inside this compartment here, right? And then we have thermometer. We know exactly the volume and the mass of the water inside. We have the thermometer. We have the specific heat. So whatever the solution did absorb is equal to the amount that was released by the reaction. So now, an important thing that I want to teach you is heat absorbed equal negative heat released. And let me explain this to you in a simple way. Let's say that the reaction released a Q that equal -5, because remember how a Q has a sign, and if it's an exothermic, then it's a negative sign. If the water going to have a change of heat, the water did absorb that, so the water heat will be 5. Now I cannot say that -5 equals 5. Mathematically this is not acceptable, but I can say that -5 equal negative the 5 value which was absorbed, and that's mathematically acceptable. So therefore, when I'm going to write an equation, I always start by saying Q released equals negative Q absorbed. So why is this? Because Q released equals -5. Negative, what is a Q absorbed? The Q absorbed equal 5, but -5 will equal -5. So I always have to put a negative here, and that's why we say QA equals negative QB. Q released equals negative Q absorbed. You will see what I mean when we solve a question in the next part. A 13.25 metal pellet at 54.36 degrees Celsius is placed in a calorimeter containing 100 milliliter of water at 20.35 degrees Celsius. The temperature of the system rises to 22.57 degrees Celsius. What is the specific heat of the unknown pellet? So to make like a shorter, less complicated version of this question, you have a cup of water and you inserted a hot piece of metal inside. What's going to happen? The piece of metal will get colder and the water will get warmer. Why is that? The piece of metal released heat, lost heat, and the water absorbed that heat. Eventually, they all equilibrate at the same temperature, which will be cooler than the initial metal and warmer than the initial water. So how am I going to solve this question mathematically, taking advantage of that simple concept of loss and heat and gain of heat? What I'm going to start writing is this. I'm going to say heat absorbed by water equals negative heat released by the pellet. Now, how do I say that? It means that Q for water equals negative Q for the pellet. Now, what does a Q for water equals to? Mass of water times specific heat of water times delta T for water equals negative. What is a Q for pellet? It will be mass of the pellet times specific heat of the pellet times the change in temperature of the pellet. Let's see what we have. Mass of water. Do I have mass of water? I do not have mass of water. I have volume of water. However, if I started with a volume of water and used the density of water, which I should know, 1 gram for every 1 milliliter. So now I'm converted, and this is water, converted volume into mass of water, times the specific heat of water, which is 4.184 joule for every gram degree Celsius, times delta T. What is delta T for water? The delta T for water is the final temperature here is 22.57, so that will be 22. That's the final temperature that water did reach, minus initially water was at 20.57 degrees Celsius. This is equal to negative, so I'm going to put this in the second line here, negative, and then what is the mass of the pellet? The mass of the pellet will be 13.25. Specific heat of the pellet is what's missing and I would like to solve, times what is the change of temperature of the pellet? The final temperature of the pellet is 22.57 minus initially it was at 54.36 degrees Celsius. So now if you look at this equation, you only have one missing part, which is the specific heat of the pellet. You have everything else available to you, and the only thing you need to solve is S for the pellet. However, you took advantage of Q water equal negative Q pellet, or you also can say Q pellet equals negative Q water. Both will be good. Now let me do the math here so you actually can do the math yourself and double check that you're doing the math correctly. So the answer will be 2.21 joule. per gram per degree Celsius. And let me write it again here. Maybe I'll put it somewhere here so you guys can see it. 2.21 joule for every gram every degree Celsius. Okay, and I corrected here the temperature, initial temperature for water. It was 20.35 degree Celsius. All good. All right, let's see this problem. A 30.14 gram stainless steel ball with a specific heat of 0.4740 joule for every gram every degree Celsius at 117.82 degrees Celsius is placed in a calorimeter containing 120 ml of water at 18.44 degrees Celsius. Calculate the final temperature of the water. Again, you have a hot steel ball inserted in water. There is a heat transfer. The ball did lose heat and water did gain it. So the way I start writing this, I'm going to say heat gained by water equal, remember, negative, always negative, heat lost by steel. Now, that means that Q water equals negative Q steel. How do I calculate Q water? It's the mass of water. Do I have mass of water? No, but I have volume of water. So 120 milliliter. I'll multiply this by the density of water, which is 1 gram of water for every milliliter. And then the specific heat of water, 4.184 joule for every gram every degree Celsius. And then delta T for water, which is, I know initially water was at 18.44 degrees Celsius, but what was the final temperature? That's what I want to calculate. T final minus initial was 18.44 degrees Celsius. This is equal to, I'm going to put it in the second line, negative Q of steel. How do I calculate Q of steel? I have 30.14 grams times the specific heat, which is 0.4740 joule for every gram every degree Celsius, times the final temperature of the steel. I don't know, but I know the initial temperature of the steel was 117.82 degrees Celsius. Now please pay attention to the following. The final temperature of the water has to be the same as the final temperature of the steel. So now I'm going to rearrange this mathematically to make my equation easier here. So I'm going to multiply. I'm going to show you what I'm going to do here so you guys can follow me. I'm going to multiply all these numbers together and then multiply by final temperature and then the negative 18.44 degrees Celsius. So mathematically that should look something as, if I have 30.14 times 0.474, that will give me 14.3 T final, and then you multiply that number by 18.44 negative 263 equals 2. Now you have the negative sign, And you're going to do the same thing for the other part. So you're going to multiply these numbers and distribute them for TF and negative 117.82. So let's do this. So if I multiply $30.14 1 second here. I think I'm gonna just back up for a second and just do this math again. I'm sorry, I think I just mixed up two numbers. So let's go back to step 1 here. So I'm going to multiply these here, and that means I'm gonna have 120 times 4.184, and that will be 502 TF minus multiplying this by 18.44, so that will be 9,260 equals to negative, now the second part, so I have 30.14 times 0.474, so that will be 14.3 TF, and then multiplying this by negative 117.82, so that will be negative, that will be a positive, so you will have 1,683. So now if you get let's just color code for a second. If you get the TFs together at one side, that means you're going to have 502 plus 14.3, so that will be 516 T final equals to, you're going to take the 9,260 to the other side and add it to 1,683 plus 9,260, that will be 10,943. If you calculate the final temperature, it will be 21.2 degrees Celsius. And it does make sense. It's higher than the initial temperature of water and lower than the initial temperature of the steel. Next question, I have 192 grams of methanol that was burned in a calorimeter containing 2.49 kilogram of water. The temperature of the water rose from 20.34 degrees Celsius to 24.54 degrees Celsius. Calculate the molar heat of combustion. Okay, so I have 1.92 grams of methanol that was combusted. That combustion released a heat. That heat was absorbed by water. So let's see here. Do I have the mass of water? I do. Do I have the specific heat of water? I should know that. And I have delta T. So what I'm going to start saying is like, okay, heat absorbed by water equal to the mass of water. I have 2.49 times 10 to the power 3 grams of water, because it's in kilograms, so I have to multiply by 1,000 to convert it to gram, times 4.184 joule for every gram every degree Celsius. That's the specific heat of water, times the change of temperature. So the change of temperature was 24 is my final, 0.54 minus the initial 20.34 degrees Celsius. Let's do the math. So I have 2.49 times 10 to the power 3 times 4.184 times the change of temperature is 24.54 minus 20.34. So now if I do the math, and I'm gonna have 3 sig fig, the answer will be in joule, so it will be let's just for convenience here, do they ask for the molar heat? Okay, so for convenience here, because this number is going to be large, I'm going to convert it into kilojoules. So I'm going to say for every kilojoule there is 1,000 joule. So if I divide by 1,000, the answer will be 43.7 kilojoule. Okay, so when I burned this much of methanol, that was the amount of heat that was released. They are asking what will be the molar heat of combustion. What does that mean? It means this is what you got when you burned 1.92. I want to know how much you will get if you burn a mole. So what I'm going to do in this case, I'll just be playing with my units. So the heat that I got is 43.7 kilojoule for every 1.92 grams of methanol. Can I make grams per mole? All I need to do is to use the molar mass. I know that. So the molar mass of methanol will be 16 for oxygen plus 4, that's 20. Add 12 to 20, that's 32. So that will be there are 32.05 grams of methanol for every 1 mole of methanol. So what I ended up having here, I canceled the grams of methanol, and now I'm going to have heat per mole. So all I have to do right now is to divide the 43.7 by 1.92 and multiply that by 32.05, and that will be 730 kilojoule per mole. That is the molar heat of combustion. That does conclude the calorimeter lecture, and I will see you next with the standard heat of formation and Hess's law.